Welcome to OP's Math e-Pathshala.
So vector. So this is the second lecture of vector spaces, part 2. So in the previous lecture we have already discussed about the definition of vector spaces and some examples. Today I would like to start by giving an example which is not a vector space. So what is the example? Suppose V is the set of all points in R2 such that x2 is x1 plus 1. So V is the set of, it is a subset of the plane R2, two-dimensional plane R2, such that x2 is x1 plus 1. That is, we have considered a straight line not passing through the origin. What is the straight line? Can you draw this straight line in the plane? What is it? So this looks like the straight line y equal to x plus 1. Yeah, y equal to x plus 1. So what would be the straight line? It would be so it will be so if we write down it in the intercept form, then it will be x by minus 1 plus y by 1 equal to 1. So that means, so it is minus 1 comma 0 and it is 0 comma 1. So joining these 2 points, so this is your straight line. So we are considering this straight line. So this is your V, and you see that from the diagram, from the picture, that 0 0 is not in the plane, in the line, sorry. So since 0 0 is not, now 0 0 is not in the straight line, that is, it is not included in V, so one can say that, so we can say that V doesn't form a vector space with respect to the usual addition and scalar multiplication induced from R2. We have already discussed about the usual vector addition and scalar multiplication on R2, and we induce these operations on V, with respect to which V will not form a vector space, as because 0 0 is not included in the set V. Because first of all, whenever V is a vector space, then it must be it needs to be an abelian group with respect to addition. So that is needed. And 0 0 was the additive identity of R2. So that space V must be a additive subgroup of R2, but which is not the case in V, because 0 0 does not belong to V. Okay, so this is an example of a set which is not vector space with respect to usual addition and scalar multiplication induced from R2. But if we consider this set, suppose such that where x2 is lambda x1, where lambda being a non-zero scalar, it is again a subset of R2, and not only that, it is again a straight line. It is again a straight line. And maybe we can draw this line. Yeah. So this is your y equal to lambda x. This line. And this line is passing through 0 0. So there is a possibility of V to be a vector space with respect to usual addition and scalar multiplication. And indeed it is. It is a vector space with respect to usual addition and scalar multiplication induced from R2. This is a vector space. Then V is a vector space with respect to usual addition and scalar multiplication induced from R2. So thus we have seen two examples. The first one is not a vector space, that is a which was a straight line not passing through 0 0, and the second one is a vector space with respect to usual addition and scalar multiplication induced from R2, which is again a straight line, but it is passing through 0 0. Later we will find out the subspaces of R2, R3, Rn, and we see that. So we shall see that these subspaces, the subspaces will pass through the origin. Yeah. Okay. Now we shall list off some simple facts which follow almost immediately from the definition of a vector space. So these facts are important, although it is not very much hard to prove. So what are the properties? properties. So first of all, we need to consider a vector space. Let V be a vector space over the field F. Yeah. Then we have first one is for any scalar lambda belongs to the field F, lambda theta must be theta, where theta is a okay. Hello. Yeah. So lambda theta is theta. Okay. Now the second one is if we consider the 0 of the field F, then 0 dot any vector V. So it will be theta for any vector V belongs to capital V. Third one is if lambda V equals to theta for lambda belongs to F, lambda be a scalar and V be a vector, then we shall get one of the following. Either this lambda will be 0 or V is a 0 vector. So thus if lambda V equal to theta, then either lambda is 0 or V equal to theta. Number 4 minus 1 dot V, then it will be the additive identity of the vector V. So the proofs are very simple. So note that the first one is lambda theta. So lambda theta can be written as lambda theta plus theta. Then by the definition of vector spaces, with the help of the axiom, so we will have it is lambda theta plus lambda theta. Then we shall cancel out one lambda theta from both sides, or you can add minus lambda theta to both sides. You will have lambda theta will be theta just by adding minus lambda theta to both sides. Yeah. So this is simple. Number 2, what is the number 2 property? That is 0 dot V equal to theta. I will leave it to you to check this property. That is 0 dot V equal to theta. Very simple. Check on your own. Number 3, now let lambda theta, lambda V equal to theta. So lambda V equal to theta. So suppose the scalar lambda is non-zero. Now since lambda be a non-zero scalar and F is a field, so lambda inverse exists. So lambda inverse exists. And with the help of lambda inverse, what will we do? We just multiply scalar multiply lambda inverse with this lambda v. Then it will give lambda inverse dot theta, which has been proved to be theta in 1. So in the left hand side we shall get, so it is lambda inverse lambda v. So by the axiom of vector spaces, it is lambda inverse lambda dot v. So it is theta. So this proves that it is 1 dot v equal to theta. Then by the axiom 4 of vector spaces, it is v equal to theta. So thus, if lambda is a non-zero scalar, then v must be theta. Or if v is non-zero vector, then lambda will be non-zero. Lambda will be 0. So this proves that v belongs to capital V, then that is v be a vector, then we shall have v plus just minus 1 v. Then v can be written as, this one will be written as 1 v, and it is minus 1 v. Then by the axiom of vector space, we will have 1 plus minus 1 dot v, and 1 plus minus 1 is 0, and 0 dot v is theta. So v plus minus 1 dot v is theta. That means minus 1 dot v is the additive identity of v. So this proves the fourth case. Okay. Now note that the associativity and commutativity of vector addition. So these two features of vector addition in a vector space V, it will leave a sum of finitely many vectors. That is, if we consider, suppose we are considering 6 vectors, suppose one is v1, v2, v3, v4, v5, v6. Suppose we are considering 6 vectors, then their sum will be independent of the way in which these vectors are combined and associated. That means v1, v2, v4, v3, v6, v5, this finite sum is equal to v1, v2, v3, v4, v5, v6. Again, you can change the combination v2, v1, v3, v5, v4, v6, and there are many other possibilities of combinations, but every such sums are equal due to the associativity and commutativity of vector addition in a vector space. Okay. And for this reason, we shall write down the sum of these vectors as v2, B3, B4, B5, B6. Simply this. Okay. So this is a special note. Now, I would like to introduce the notion of linear combination of vectors, which will be an important tool to characterize the subspaces and dimensions basis of a vector space. So let us introduce the linear combination of finitely many vectors. Suppose let V be a vector space over a field F. So you must write down each time whenever you are considering a vector space, you must write down that it is a vector space over a field. That is important. Because we need to consider the scalar multiplication with respect to this field. Now a vector V belongs to capital V. It is said to be a linear combination of some vectors, suppose v1, v2, vn in V. When do we call a linear combination of these vectors? If you can find out n many scalars, lambda 1, lambda 2, lambda n, in F such that V will be represented as lambda 1 v1, lambda 2 v2, lambda n vn. So in this way, the linear combinations of vectors, of finitely many vectors, will be formed. Now, certain extensions of the associativity of vector addition and the distributive properties of scalar multiplication can be obtained by applying to linear combinations. Okay. Yeah. Now, in the scheme of generating new vector spaces out of the old ones, out of the old known vector spaces. So this is our basic goal, to construct new vector spaces from the known vector spaces. And in this line, the next definition is very much important, because we are considering the subspaces of a vector space, so which will be a new vector space from the old one, by considering the non-empty subsets of the vector spaces. All vector spaces so we are considering non-empty subsets of the vector spaces with respect to their induced operations. The operations which lies in the vector space itself. So we shall consider these operations and we will impose these operations on the subsets, non-empty subsets. And subspace of a vector space can be defined as follows. So a subset W of a vector space V is said to be a vector subspace or simply a subspace of V if W itself forms a vector space over F, over the field F, with respect to the same operations induced from V. Same operations induced from V. Induced from V. So that means W is a subspace of V if it itself forms a vector space over the same field of scalars F with respect to the same operations which has been defined on V. Then W is called a vector subspace or simply a subspace of the vector space V. And we have already seen an example, the line passing through, suppose y equal to x. So this is a line passing through 0, 0 in R2 and making an angle 45 degree pi by 4 with respect to the positive x axis. And this line is a vector subspace of R2. And you can consider any straight lines passing through 0, 0. Each of them will form a vector subspace of R2. So whenever you are asked to give an example of a vector subspace of a vector space, you may always place these examples. So these are basic examples of vector subspaces. And the condition for which a subset will form a vector subspace is the following. That is, for any arbitrary vector space and given any non-empty subset of a vector space V, whenever you see that these conditions it has been satisfied by the set W, then you can say that W is a vector subspace. What are the conditions? The next theorem will state these conditions. That is, a non-empty subset W of a vector space V is a subspace of V. Empty subset W of a vector space V is a subspace of V if and only for each pair of vectors VW belongs to capital W and for each scalars lambda belongs to F, the vector lambda V plus W is also in the subset or equivalently if and only if just one can split these conditions into two conditions, and these are if and only for all vectors V comma W belongs to W, and for all scalars lambda belongs to F. The first one will be V minus W belongs to W, and the second condition is lambda V belongs to W.